all student came 21. Okay, perfect. Let me share the screen. Let me know if it is visible or not. Okay.
In this video, we'll try to understand how to draw shear force diagram and bending moment diagram in case of
Screen is
simply
visible.
supported beam carrying uniformly distributed load. Now the arrangement of the beam is as shown over here.
Screen is visible. Audio
The
video is
UDL
okay.
of 50 kilonewton per meter is acting for a distance of 2 meter from the left hand support A, and a uniformly
Hello.
distributed load of 20
Am I
kilonewton per
audible?
meter is acting at a distance of 2 meter from the right hand support B.
Yes, ma'am.
Now
Okay,
first thing we
video
have to
and
find
audio
out
is
these
fine.
reactions RA and RB.
Yes, ma'am.
Okay,
So we'll
okay.
convert this
So see, in the
in this
last
video
class
we'll
we
try.
discussed about your simply supported beam with point load and UDL also, right? So this is also a simply supported beam, but with two different UDL. Okay, one is 50 kilonewton, another is 20 kilonewton at different positions. From A to C, UDL is given as 50 kilonewton per meter. From D to B, a 20 kilonewton meter is given. Okay, same simply supported beam with UDL at different positions. Okay, so we'll see these type of problem today. So let's continue.
To understand how to draw shear force diagram and bending moment diagram in case of simply supported beam carrying uniformly distributed load. Now the arrangement of the beam is as shown over here. The UDL of 50 kilonewton per meter is acting for a distance of 2 meter from the left hand support A, and a uniformly distributed load of 20 kilonewton per meter is acting at a distance of 2 meter from the right hand support B. Now first thing we have to find out these reactions RA and RB. So we'll convert this particular uniformly distributed load into a point load. So the meaning of UDL is for 1 meter length the load that is acting is 50 kilonewton, then for 2 meter length the load that is acting will be 100 kilonewton, and it will be acting at the center of this rectangular distribution. Similarly over here also the UDL load will be 20 into 2, that is 40 kilonewton, and will be acting at the center of this rectangular distribution. So we have converted that uniformly distributed load into point load. Now this point load is acting at the center, so over here it will be acting for a distance of 1 meter, and over here also it is acting for a distance of 1 meter. Now we'll apply the conditions of equilibrium to find out the reactions. The first condition of equilibrium is summation of Fy is equal to 0, that is summation of forces in y direction is equal to 0. Upward forces are positive and downward forces they are considered as negative. Now RA and RB they are acting in the upward direction, so they are considered as positive, whereas this 100 kilonewton load it is acting in the downward direction. This 40 kilonewton load that is also acting in the downward direction, so that is equal to 0. So we can say that RA plus RB is equal to 140. Now we'll apply the another condition of equilibrium, that is summation of moments is equal to 0. Clockwise positive and anti-clockwise moments will consider negative. Now start from this RB. The arrow of this reaction RB will be going in the anti-clockwise direction towards A. So it is minus RB, and from B to A the perpendicular distance is 6. So it is minus RB into 6 because it is in the anti-clockwise direction. This 40 kilonewton point load will produce the clockwise moment towards A, so or about A, and the perpendicular distance from this point up to A will be 2 plus 2 plus 1, that is 5, and as it is clockwise it is positive. Similarly this 100 kilonewton load that will also produce the clockwise moment, so it is 100 into 1. So we can say that 40 into 5, that is 200 plus 100, so it is 300, and transfer is negative term on the other side, so we will get the value of RB as 50 kilonewton. Now substitute that value of RB in equation 1, so we'll get the value of RA also, so it is 140 minus RB, so that is 90 kilonewton. So the reactions we have calculated as 90 and 50 kilonewton. Now we have to draw the shear force diagram. The conventions for drawing the shear force diagram are: upward forces, they are considered as positive, whereas downward forces, they are considered as negative. So shear force at A will be 90 kilonewton, and this is acting in the upward direction, so it is positive. Shear force at the left of the C, we have to consider all the forces which are acting on the left of the C. So RA, which is acting in the upward direction, so it is positive, and 50 into 2, that is the 100 kilonewton, that is acting in the downward direction, so it is minus 10 kilonewton. The same shear force will act at point C also, because there is no other point load that is acting at point C. Now between C and D, there is no other force that is acting on the beam, so whatever the shear force that we have calculated at point C, the same will remain at point D also. At the left of the B, we have to take into consideration this uniformly distributed load of 20 into 2. So it is minus 10, which we have obtained up to point D, and to that we have to add 20 into 2 in the downward direction, that is 40 kilonewton. So minus 10 minus 40, that is minus 50 kilonewton. But exactly at point B, there is another reaction which is acting in the upward direction, so minus 50, which we have calculated earlier at the left of the B, and to that we have to add upward reaction 50 of 50 kilonewton, so it is 0 kilonewton. Now using these values, we can draw shear force diagram. So first we'll draw the baseline or a reference line. Shear force at A is 90 kilonewton. At left of the C and C, it is minus 10 kilonewton, remains same up to point D. Then at left of the B, it is minus 50 kilonewton, and at exactly at B, it is 0. So the respective values we have already written on this particular diagram. Now we have to draw the bending moment diagram. Before that, we'll find out the point of zero shear. So this is the point of zero shear, where shear force diagram, it changes the sign from positive to negative. So consider this section at a distance x from A as shown over here. Now we'll concentrate only at that particular section. So to find out the point of zero shear, so concentrate on this section x6 acting at a distance x from the left hand support, that is A. So on the left hand side of this section x6, the forces which are acting is RA, which is acting in the upward direction, that is positive, minus 50 into x. So as it is acting in the downward direction, it is negative, and the shear force is 0 at this particular section. Transfer this negative 50 term on this side, it will become positive, so x will be equal to 90 divided by 50, that is 1.8 meter from A. Now on this particular point of zero shear, the bending moment will be maximum, so our next job will be to find out the value of maximum bending moment. So we'll convert that particular UDL into a point load acting at the center of this x, that is x by 2. So 50 into x is the UDL, and acting at the center of x, that is x by 2. And now we have to find out the moments about this particular section x6. So consider all the forces on the left hand side of this x6. So 90, which is the reaction RA, will produce clockwise moment about section x6, so it is 90 into x, and this 50x will produce anti-clockwise moment about this particular, so it is 50 into x by 2, so that is negative because it is producing anti-clockwise moment. So we can say that bending moment at this particular section x6 is 90x minus 50x square upon 2, or substitute the value of x, that is 1.8. So at this particular x is 1.8, here also it is 1.8, so we will get the value of maximum bending moment as 81 kilonewton meter. Now we'll find out the bending moment at the various other section. Now we know that bending moment at point A will be 0 because there is no force that is acting on the left hand side of A. Bending moment at XX we have already calculated, that is 81 kilonewton meter. Now we have to find out what will be the bending moment at point C. So we have to consider all the forces which are acting on the left hand side of C. So on the left hand side of C we are having RA, that is 90 kilonewton, and it is producing clockwise moment about C. So it is 90 into 2. The perpendicular distance between A and C is 2. Then the UDL 50 into 2, that is 100 kilonewton, and it will be acting at the center of 2 meter length, that is 1 meter, but that will be producing anti-clockwise moment. So it is minus 100 into 1. So 90 into 2 minus 100 into 1, so that comes out to be 80 kilonewton meter. Now bending moment at point D, again consider all the forces which are acting on the left hand side of A. So this is 90, and from A to D the perpendicular distance is 4, so it is 90 into 4. This 100 kilonewton, it will produce anti-clockwise moment about point D, so it is 100 into 1 plus 2, that is 3. So this 100 kilonewton from this point up to point D, the perpendicular distance is 1, this 1 plus 2, that is 3, so it is 60 kilonewton meter. Then bending moment at point B will be 0 because there is no other force that is acting on the right hand side of B. Correct? Or even if you calculate considering all the forces on the left hand side, the value that will become will be, the value that comes out will be 0. So at end points there will not be any bending moment. Now we'll consider all these particular values and then we'll draw this bending moment diagram. So at A it is 0, then from A to C there is UL which is acting, so there will be a parabolic curve because it is the second degree equation that will obtain. Now within that we are having the bending moment at this section XX, which we have already calculated, and it will be maximum, it is 81 kilonewton meter. So out of all the values you can see that the bending moment at section XX where shear force is 0 is always maximum, that is 81 kilonewton meter. Then from C to D there is no load that is acting, so there will be a straight line, and there will be again a parabolic curve from D to B because this is the second degree equation that will obtain over here as there is a UDL. So in this way we can draw the shear force and bending moment diagram in case of simply supported beam carrying uniformly distributed load. Thank you very much for watching.
So have you understood this part? The first step will be the same to find out the support reactions, okay, by using equations of equilibrium, uh, uh, summation of all the vertical forces, summation of all the horizontal forces, and summation of moment about a point will be equal to 0. Okay, that will be the same procedure of finding out the support reactions. Okay, so they have found out the support reaction RA and RB 50 and 90 kilonewton. Then the next step will be to draw the shear force at every point. Shear force at A, shear force at left of C, shear force at C. At C there will be two load RA and this UDL. Then from C to D, like this, there will be different shear force at different points. So these are the points where we need to find out the shear force. more the number of points, number of this A, C, B, D, more will be your shear force values. Okay, so from these values you have to draw this diagram. This is called as shear force diagram. Okay, place the values. Then again you can find where your shear force will be 0. Okay, you can take a section. They have taken a section. Then they have equate the equation equals to 0. They have found out the shear force equation on this part and equated this equation equals to 0 to find out a distance x. That means 1.8 meter. That is from A 1.8 meter, the shear force will be 0. So if you see the diagram, yes, from 1.8 the shear force is 0. Again, the next step will be to find out the bending moments at different points. Bending moment at A, like this, you can find out the bending moment also for different points. So here, bending moment will be at A, bending moment will be at C, and bending moment at will be D. Okay. Still মানে লিপস্টিক তোমার নিজে লগাইছে তাই দিয়ে নাই তাই দিছে তাই মানে এনেকুৱা কালাৰ আছে এটা এইটো কালাৰ লিকুইড দিলে ঠিকই আছে একো বেয়া লগা নাই তো আৰু নিজে ভাবি আছে so this is the bending moment diagram. Okay, so any issues, any doubts from this part, this numerical? Any issues, any doubts from this part of this numerical, from this numerical, at any point? ফুল যিমান দিছিল গুটি লগাই দিছে হা এই মানে ফুলৰ বাঞ্চ এটা কিনে তাই হেনুকা ভালকে হোৱা নাই মতো ধুনা আছে Am I audible? If you don't have any issue, you can at least type in the chat box, no issues, no doubts, right? What about others? Huh? Abrisha, Deepak, Jodha, John. I won't repeat this class, okay? If you have any issue, you ask me right here. If you don't have any issues, then I'll move forward. Okay, I'll share the next problem, okay?
In this video, we'll try to understand how to draw shear force diagram and bending moment diagram in case of a simply supported beam.
Is the audio and video is fine?
Distributed load over the entire span length.
Yes, ma'am.
Okay, thank you. Only you are replying. So in this beam, this is also simply supported beam. At this position, it has some overhang part. Okay, so in this we'll find a point of contraflexure. That means your simply supported beam carrying UDL distributed load over the entire span and having an overhang. So here UDL is acting over the whole span and this part is overhang. So let's see how to solve, and we'll see a new word to find a point of contraflexure. Okay, so let's continue. Then I'll discuss in the midway. Okay.
The right hand side. Now the arrangement of the beam is as shown over here. So the beam is of 6 meter length and there is a overhang of 2 meter which is provided on the right hand side of the beam. Now on the entire span length of 6 meter there is a uniformly distributed load of 8 kilonewton per meter that is acting. Now for this particular arrangement we have to find out first the beam reactions. So first we'll convert this uniformly distributed load into a point load. Now we know that the meaning of 8 kilonewton per meter is that for 1 meter length the load that is acting is 8 kilonewton. Then for 6 meter length on which that UDL is acting, the load will be 8 into 6, that is 48 kilonewton. Now, as this is the rectangular distribution, the load will be acting at the center or centered of this particular rectangular distribution, that is 6 upon 2, that is 3 meter length. So first we'll convert this uniformly distributed load into a point load. So 8 into 6, that is 48 kilonewton, and it will be acting at the center of 6 meter length, that is 3 meter. So now we'll apply the conditions of equilibrium to find out the beam reactions. So applying the conditions of equilibrium, the first condition is summation of forces in y direction is equal to 0. Upward forces we have considered them as positive, whereas downward forces we have considered as negative. So RA is considered as positive. RA is positive, which is acting in the upward direction, and RB is also positive. 48 kilonewton, it is acting in the downward direction, so it is negative. So RA plus RB minus 48 is equal to 0. Transfer this negative term on the other side, so it will become positive. So this is our first equation. Now we'll apply the another condition of equilibrium, that is summation of moments is equal to 0, clockwise positive and anti-clockwise negative. So we'll take the moment about point A. Now start with this reaction RB. So this RB will produce anti-clockwise moment about A, that is indicated by this particular arrow, and the perpendicular distance between B and A is 4 meter. So minus RB into 4, that will be the moment that will be created by this reaction RB, which is acting in the upward direction. Now this 48 kilonewton load, point load, will produce the clockwise moment as indicated by this arrow about A. So 48 and the perpendicular distance is 3 meter from the point of application of the load up to A. So 48 into 3, and it is clockwise, and hence it is positive. RA will not produce any moment because it is already passing through point A. It is not having any perpendicular distance. So 48 into 3, that is positive moment, and RB into 4 is a negative moment. So anti-clockwise moments are negative and clockwise moments they are positive. So 48 into 3, that is 144. Transfer this negative RB into 4 term on the other side, it will become positive. Now divide by this 4 on this side, so it is 144 divided by 4, that is equal to reaction at point B. So RB will be equal to 36 kilonewton. Now we have to find out the value of RA. So from equation 1 we can say that RA will be equal to 48 minus RB. Now just substitute the value of RB, that is 48 minus 36. The value of RB that we have calculated is 36. So 48 minus 36, that is 36, that is 12 kilonewton. So in this way we can find out the beam reactions in case of a simply supported beam carrying UDL. Now we have to make the calculations for shear force. So shear force diagram calculations. The conventions which we have used are upward forces are positive and downward forces they are negative. Now shear force at A. At A there is a reaction RA which is acting in the upward direction. So shear force at A is 12 kilonewton because it is acting in the upward direction. Shear force just at the left of the B. That means we are not considering this particular reaction 36. We are just considering all the forces which are acting on the left hand side of B, that is RA and this UDL. So RA which is acting in the upward direction, that is 12 kilonewton, and UDL from A up to just left of B is 4 meters. So 8 into 4, that is 32. So 12 minus 32, that is minus 20 kilonewton. Now shear force at B. To this minus 20 we have to add the upward acting reaction which is positive, that is 36 kilonewton. So 36 minus 20, that is 16 kilonewton. Now shear force at C. So up to B we are having 16. So 16 that we have written over here, and from B to C UDL is 8 kilonewton per meter acting over 2 meter length. So 8 into 2, but it is acting in the downward direction, so it is negative. So 16, that is from the previous value is 16 minus this UDL load of 16. So 16 minus 16, that is 0 kilonewton. So let us draw this shear force diagram using these particular values. So first we'll draw the baseline. Then at A the shear force is 12 kilonewton. Then it decreases to minus 20 kilonewton. Then at point B it is 16 kilonewton and again reduces to 0. So these are the various values which we have indicated over here. Now this is the important point. This is the point of zero shear, and first we'll find out this particular point of zero shear. Now we'll consider the principle of similarity of the triangle. So this particular triangle is having base of x and height of 12, and this is having, so this distance is 4, so this base will be 4 minus x, so 4 minus x and height is of 20. So using this concept, we can say that x upon 12 for this triangle will be equal to 4 minus x divided by 20. That is, base divided by height is equal to base divided by height for the another triangle. So x upon 12 is equal to 4 minus x divided by 20. So that we have indicated over here. Now cross multiply. So 20 into x will be equal to 12 into bracket 4 minus x. So we have cross multiplied these two particular terms. So 20x will be equal to 12 into 4, that is 48, and 12 into minus x, that is minus 12x. Now transfer this negative term on the other side, so it will become positive. So 20x plus 12x, that is 32x, and that is equal to 48. So therefore x will be equal to 48 divided by 32, that is 1.5 meter from A. So we can say that the value of x is 1.5 meter from A, where shear force is becoming 0. Now we'll find out the bending moment at this particular point of zero shear. So let us extrapolate that particular section and let us call this as section XX in our original diagram. So x distance we have already calculated. Now we have to find out what will be the bending moment at this particular section XX. So just we'll consider the forces on the left hand side of this particular section XX. So we'll remove this 8 kN per meter load which is present on the right hand side of this section XX. So 8 into x, that will be the UDL which we have which will be converting into the point load. So 8 is the UDL and multiplied by distance x, and it will be acting at the center of that particular x distance, that is x by 2. So these are the loads which are acting on the left hand side of this particular section XX. So bending moment at the point of zero shear. So RA will produce the clockwise moment. So arrow, upward acting arrow of this RA will produce the clockwise moment about XX. So it is RA into X. So that we have mentioned over here. Whereas this downward acting arrow of 8x will produce anti-clockwise moment about section XX. So it is 8x into x by 2. So now substitute the value of x over here. So x is 1.5. So here also x is 1.5 and this is 1.5 upon 2. So if we make the calculation, then it will be 9 kilonewton meter. Now the bending moment calculations that we'll perform over here. At the end points of the simply supported beam, the bending moment is 0. So at A it is 0. Similarly, bending moment at C also it is equal to 0. The conventions that we are using is clockwise positive and anti-clockwise negative. Bending moment at section XX, that is the point of zero shear, already we have calculated, it is as 9 kilonewton meter. Now we have to find out what will be the bending moment at point B. So we have to consider all the forces which are acting on the left hand side of B. So on the left hand side of B, we are having reaction RA which is acting in the upward direction and UDL of 8 kilonewton per meter acting for 4 meter length. Now reaction RA will produce clockwise direction because the arrow of RA is acting in the upward direction. So it will go in the clockwise direction towards B, and the perpendicular distance between A and B is 4 meters. So it is RA into 4. Whereas this 8 into 4, it is the UDL which we are converting into point load, and it will be acting at the half of this 4 meter length. So 8 into 4 into 2. So that, but as it is acting in the downward direction, it will produce the anti-clockwise moment about point B. So 8 into 4 into 2, that will be the moment of the UDL load, and that value comes out to be minus 16 kilonewton meter. So let us first draw the baseline. Bending moment at A it is 0. At XX it is 9 kilonewton meter. At point B it is minus 16 kilonewton meter, and at C it is again 0. So it is a parabolic distribution because this is the second degree equation. Now the bending moment diagram is changing its sign. So at this point the bending moment value is becoming 0, and that particular point is known as point of contraflexure. So first we'll find out the point of contraflexure. So suppose we extrapolate this and we'll call this as section YY at a distance of Y from A. So we have to find out the point of contraflexure. So bending moment at point YY. So again, we have to consider all the forces which are acting on the left hand side of this section, that is YY section. So on the left hand side of this section YY, there is upward acting reaction, that is RA, and the UDL of 8 kilonewton per meter acting for Y meter length. So again, RA will produce, it is the upward arrow, it will produce the clockwise moment about YY. So it is RA into Y minus, so this is RA into Y minus 8 into Y, it is the UDL load, and it will be acting at the center of Y meter length, that is Y by 2. But as it is in the downward direction, this will produce anti-clockwise moment about this particular section. So RA into Y minus 8 into Y is the UDL load and acting at the center of Y, that is Y by 2. So 8 upon 2, that is 4, so it is 4 y into y, that is y square. So RAY minus RA into y minus 4 y square, and bending moment is 0. Transfer this negative term on this side, so it will become positive. Now cancel out one y term from both the sides, so it is 4 into y is equal to RA, or we can say that y is equal to RA divided by 4. Now value of RA is 12, so 12 by 4, so it is 3 meter from A. So we can say that point of contraflexure will lie at a distance of 3 meter from A, where bending moment diagram is changing its sign from positive to negative, and this is the point of contraflexure. So in this way we can find out the beam reactions, we can draw the shear force and bending moment diagram, and we can find out point of zero shear as well as point of contraflexure in case of a simply supported beam carrying uniformly distributed load over the entire span length and having a overhang on the right hand side. Thank you very much for watching.
So in this problem, the first step will be the same to find out the support reactions. Okay, what they have done, they have converted this UDL into a point load and placed, as this point UDL is spanning over the whole span, so they have replaced this UDL with point load and placed at the midspan of the beam, right? So it is total 6 meters, so they have placed the point load at 3 meter to find out the support reactions. Okay, now by using equilibrium equations, they have found out the RA and RB. Okay, by using summation of all the vertical forces movements, they have found out the RA and RB. So that will be your first step. Okay. So after finding out the support reaction, they have found out the shear force at different points. The procedure will be same. Okay, this is the shear force diagram for this kind of beam. Now the point is point of zero shear, where your shear force is 0. You can find out from diagram also. Okay, if you see this figure, this is a symmetrical figure, so they have equated this x by 12, that means this distance. Give me a minute. So they have equated this part x by, these two are similar triangles. Okay, this and this is the similar triangles, so they have equated x by 12 is equals to 4 minus x by 20. So you can find from this figures also the point. Yeah, yeah.
But why is not minus 20?
Where this position, they have cross multiplied now. They have not they have just cross multiplied. It is not plus and minus thing here. They have cross multiplication. They did the cross multiplication. In cross multiplication there is no chance of placing minus here. When you do here it will come. If you place this 20x to this side, then it will come minus. Now understood? this is simply the cross multiplication from similar triangles. They have found out, as these two triangles are similar triangles, so they have found out the x value from the figure. Or you can also find the earlier way, the conventional way to find out, taking a section xx. Let me note, taking a section, let me change a color, by taking a section xx and equating a shear force equation of this part, and equating that equation equals to 0, and find, you can find out x value. Okay, or you can do, as these two figures are symmetrical, they have to, so they have taken the similar triangle equations, they have placed the equations, and by cross multiplication they have found out that x equals to 1.5 meter. So at this position, x from x equals to 1.5 meter, your shear force will be 0. Okay, which is also called as point of zero shear force. Next, BM at point of zero shear force. So what will be the bending moment at zero shear force? So how to find out? So they have taken the section, they found out the bending moment equation at this point. Okay, so the bending moment at that point will be, place the value of x by replace the value of x by 1.5, because see what it says, bending moment at the point of zero shear force. So we have zero shear force at x equals to 1.5 meter. So what we have done, we have found out the bending moment equation at this part, and we have replaced that x with 1.5 meter, and we have found out that the point where your shear force is 0, what is the bending moment? The bending moment is 9 kilonewton per meter, 9 kilonewton meter. Okay, now again they found out the bending moment equation the same way at different points A, B and C. And they have drawn the bending moment diagram also. Now to find out point of contraflexure, that means where, point of contraflexure means where your bending moment will be 0. Remember, okay, MCQ question may ask, what is the bending moment at the point of contraflexure. So bending moment, the where the point, your beam has 0 bending moment, that will be considered as point of contraflexure. Okay, and you can also notice that when shear force changes sign, when you see the bending moment equations, let me okay, see bending moment is, where is the bending moment is maximum? 0, 9, minus 16, 0, right? Let me sorry, hey, just give me a minute. So see, your bending moment is maximum at 9 kilonewton, right? That means at x equals to 0. Sorry, at x equals to 1.5, your bending moment is 9. So this is the maximum bending moment you have. Okay, so always remember, when the shear force changes sign, you will have a maximum bending moment. What I'm saying, whenever your shear force diagram changes sign, so see here your shear force is changing sign from positive to negative, and at this point you will have your maximum bending moment. So one more question can be generated from this part, that when your bending moment in a beam will be maximum. So your bending moment will be maximum when shear force changes its sign. Got it? Understood this part? Okay, so I was understood this part. At least reply yes or no.
Yes, ma'am.
Yes.
Okay. So your bend. So that is another thing, and the contraflexure is that your bending moment will be 0. So take a section over a beam, find out the bending moment equation, and equate that equation equals to 0. Okay. So I have found out y equals to this. That is 3 meter from A. So at 3 meter from A, your bending moment will be 0. See, if you see the bending moment diagram here, your bending moment is 0. So that is also called as point of contraflexure, where your bending moment will be 0. Okay, go through this class once again, then you will understand. that's all for today. Next class we'll discuss cantilever beam. Okay, we'll discuss cantilever beam. So all of you can write your roll numbers in the chat box. Okay. Anyone left? 24, 22. Okay. Okay. Thank you.
Ma'am,
Yeah. Say.
ma'am, is HOD sir present today at university?
Sorry. What?
Ma'am, is HOD sir present today at
Yes.
university?
He is there. He is there.
Okay, ma'am.
Okay.
Thank you, ma'am.
Thank you.